All right, this is the last lesson of the week. It's about transformations of quadratic graphs. So what we are going to do is we are going to take our parabola and we are going to apply different rules for transformations, and we are going to move it left, right, up, down. We are going to compress it vertically, stretch it vertically. We are going to reflect it. Those transformations should be familiar for you because we've done all of those for the absolute value functions. So remember when we took the graph that looked like V and we were able to move it left, right, up, down, we were able to stretch it. The same rules apply to the quadratic functions. As a matter of fact, they apply to all of the functions. So remember in the absolute value function, we had the absolute value bars. Now we have parentheses. And now our graph is still going to look like the U shape thing rather than V. But again, the transformations are going to work in the same way. Right here on the top of the page, I am going to write very quick notes. What I do want is I want the parent graph of the quadratic function. And the parent graph looks like this. So the parent graph has the equation of y is equal to x squared. I do want to graph it, and in order to graph it, I want to figure out a couple points. Well, maybe more than couple. I will take -2, -1, 0, 1, and 2. So now if I plug in -2 into my equation, I see that I need to square it. So that is going to give me 4. -1 squared, that is going to give me 1. 0 squared, that is going to give me 0. 1 squared, that is going to give me 1. And 2 squared, that is going to give me 4. I want you to see it works exactly the same way as it did for the absolute value function. Those are the same as long as you will take the points that are the same distance from the point in the middle. I want you to see that the change in the point is different because now we are going 1 and then we are going 3. So you will see in a second how that is going to affect our graph. I want to make this graph. I want to make sure everybody has those notes on the paper, so please, to get the full credit, make sure you have them. My point 0, 0 is right here. 1 goes with 1, and 2 goes with 1, 2, 3, 4. So this is one part of the parabola. -1 goes with 1, and -2 goes with 4. I want you to remember this one rule that we are going to use in a second. From the vertex to the first point, if it's a parent graph, if the A is equal to 1, we have 1 up, 1 over, but then we have 3 up, 1 over. Okay, let's remember that because we are going to use this in just 1 minute. Okay? Now, first transformation that we are going to talk about is what is going to happen if I change A. So I am going to have 3 graphs on the first coordinate plane. The first one is going to be y is equal to x squared. The second is going to be y is equal to 2x squared. And then the third one is going to be y is equal to 1 over 2x squared. As I said before, this works exactly the same way as it did for the absolute value function. So if A is between 0 and 1, what we are going to have is our graph is going to be compressed vertically. If A is greater than 1, then our graph is going to be stretched vertically. Okay, and let's see how it looks like. I will try to color code everything, so you will see every single time we are going to start with the parent graph, so I hope everybody will be fine with this. 0, 0, 1, 1, 2 goes with 4. If I do find one more point, 3 squared would go up to 9. The same thing here. Remember, this is our axis of symmetry, so I can think about this. All right, 2 points, so 2 points, and then 1, 2, 3, 1, 2, 3, 3 points. Going from this point to this point, 1, 2, 3, 4, 5 up over 1. So first one is 1, 3, 5. All right, let's remember that. This is my parent graph. I haven't done any transformations, I just graphed the parent graph. The second one is what is happening when I have 2x squared. So this graph, because a is greater than 1, is going to be stretched vertically. So now this first point, instead of having going 1 up over 1, we will stretch it, so we will go 2 up over 1. So it's like multiplying 1 times 2. And then the next point, instead of going 3 up over 1, 3 times 2 is 6. So I will go 1, 2, 3, 4, 5, 6 up over 1. And then what I can do is I can use the symmetry and I can find my other 2 points. Here we go. This is my second graph. You can always check those points. So what would happen if I plug in 2 inside of my equation? Well, 2 squared is 4. 4 times 2 is 8. And that's exactly where our point is. Let's write down let's graph the third graph. Now what happens is, again, it's going to be compressed vertically. So instead of going 1 up over 1, we will go up 1/2 over 1. Instead of going 3 up over 1, we will go half of 3 is 1.5. So here, and then over 1. And then the next one, well, let's see, what did we say? The original one was 1, then it was 3, then it was 5. So it would be 2.5. So 1 up, 2.5 up, 1 over. We can use the symmetry. This point is going to go here. I am 1, 2 away, 1, 2 away, and so on. Again, oops, I probably shouldn't go that far. We can check what would happen if I plug in 2 in place of x. 2 squared is 4, half of 4 is 2. That's exactly where I am. If I take 3, 3 squared is 9, half of 9 is 4.5, 1, 2, 3, 4.5. That was my intention. All right, so you see how if you just change the number that is in front of the x squared, it's either compression vertically or it's stretching vertically if a is greater than 1. All right, let's do another example. Let's see a different transformation. My parent graph, y is equal to x squared. I can't emphasize enough how important it is to be able to graph this. For 1, I am at 1. For 2, I am at 4. For 3, I am at 9. I am using the axis of symmetry. So this is going here. This is 2 away from axis of symmetry. This is 1, 2, 3 away from axis of symmetry. This is my parent graph. You can again always test points. If you take -1, -1 squared is going to give me +1, -2 squared gives me +4, and this is our parent graph of the parabola. All right, what is going to happen if I now have y is equal to -1x squared? Negative sign does exactly the same thing that it did for the absolute value graphs. So -a is going to flip the graph. Okay, so now I'm in this case, because our vertex is at 0, 0, the vertex is going to stay at the same place, but this point is going to go here, this point is going to go here, 4, 1, 2, 3, 4, 4, here we go. We have our beautiful reflection of our graph, and this is what the negative sign does. All right, let's move our graphs up and down and left and right and see how that applies. Make sure you pause this video if you need to go back to those graphs when you will be working on the problem set and you don't know how to do something. Make sure you come back to those videos, all right? So let's see, 3 graphs. The first one is a parent graph. The second one that we will want to graph is y is equal to x minus 2 squared. And then the third one that we are going to graph on the same graph is going to be x plus 3 squared. I want you to see that if you look at your form, well, this form is called actually vertex form. You will learn why soon. If you look at this vertex form, what is in parentheses, that is your h. So now if you have x minus h, this is going to be shift to the right by the h amount of units. And if you have x plus h, you will have shift to the left. All right, one more time, parent graph. Let's start with the parent graph. 0, 0, 1, 1, 2, 4. So again, 1 up, 1 over, 3 up, 1 over. And then 3 goes with 9, 5 up, 1 over. Use the axis of symmetry. This is our parent graph. Okay, again, I am trying to color code them so we know which graph is which. This is our beautiful parabola parent graph. Now the next one, I want you to see what happens. This graph is going to be moved because I am subtracting. Our graph is going to be shifted to the right. So again, subtraction is shifted to the right. What I am going to do is I am going to take the vertex point, 1, 2. I am going to move it right in here. I'm going to take this point, 1, 2. I am going to put it right here. This point, 1, 2. I am going to put it right here. Or I can think about this. If I started here, the next one would be 1 up, 1 over, and then I can see this shift. The same thing here, 5 up, 1 over. This is one part of the parabola. And then the other part at this point would be moved right in here. And this point would be moved right in here. Notice how I shifted everything 2 units up. This one would be moved right in here. Not 2 units up, 2 units, 2 units right, okay? This is my transformation. I moved the vertex and I moved every single point. All right, and then we have the other one. Now I have addition, so my graph is going to be shifted to the left. Again, I am starting with my original graph, with my parent graph, and now the vertex is going to be moved 3 units this way. You can either shift the points or you can just think about this. This is not, this graph is not stretched or anything. So from here, knowing that this is your vertex, 1 up, 1 over, 3 up, 1 over, 1, 2, 3, 4, 5 up, 1 over. This is one part of your parabola, almost perfect. Again, if you don't have a printer and you don't have ability to print, make sure you make those pictures as nice as possible so I can actually read them. Here we go. So the red graph is shifted to the left. This graph is shifted to the right. All right, we will do another example together. Well, we'll do a few more examples together. We will start with the parent graph. Again, I hope by now everybody knows the parent graph. And then this one is going to be y is equal to x squared plus 2. And then the next one that we are going to do is y is equal to x squared minus 3. Notice those numbers are not in the parentheses. And if you are recalling the absolute value graphs, that was extremely important. So if the number is in parentheses, we know we shift it left, right? If the number is not in parentheses, we will shift our graph up when it's plus. So if we are adding k, notice that in our formula on the top of the paper, that number that we are adding outside of the parentheses is k. So if we are adding k, we are going to shift the graph app. If we are subtracting k, we are going to shift the graph down. All right, so let's start with, again, the parent graph, 0, 0, 1, 1, 3 up, 1 over. Always check. If I have 2 square, 4, that's fine. 1, 2, 3, 4, 5 up, 1 over. That's our pattern for what we would like to call a rate of change for the quadratic form. -1, right in here, right in here. And here's my beautiful parabola parent graph of the quadratic function. All right, now notice again, I do not have any a. I am not moving it left, right. So the only thing I am doing for this graph is I am moving it 2 units up. I'm starting by shifting the vertex. 1 over 1, 1 up, 1 over, 3 up, 1 over, 1, 2, 3, 4, 5 up, 1 over. And that is shifting all my points. You can see how this point is here, this point is here, exactly 2 units up. This point is here, this point is here, this point is here. You can look at the axis of symmetry. Axis of symmetry is right at 0. And in the last graph, I am going to shift it 3 units down. So my vertex, again, I am starting with the parent graph. 3 down, 1 up, 1 over, 1, 2, 3, 1 over, 1, 2, 3, 4, 5, 1 over. I have this piece, and then I can reflect it if I want to. 1, 2, 3, 1, 2, 3. The beauty of those transformations is that you can use them for the linear function, quadratic function, but then you will see in the future polynomial, trigonometric functions, and any other functions you are going to be learning about. All right, let's do a few more examples. So on the next page, we'll have some examples where we have multiple transformations at the same time. I am going to do some of them just to model them, but please take your time to watch this video. Please go back to it when you are working on the problem set. So first of all, you are to describe what the transformation is. So this first transformation, notice that this is your h, and because we are subtracting h, this is going to be 3 units to the right. And then the -2 is 2 units down. What I am going to do is I am going to start by graphing my parent graph, which is y is equal to x squared. And then we'll think of the transformations, and then we'll figure out what the vertex is, and then we'll figure out what the axis of symmetry is. 0, 0, 1, 1, 2, 4, again 3 up, 1 over, 3, 9, and this 2, and so on, 3, 1, 2, 3, perfect. So again, this is my parent graph. And now what I am going to do in pink, I am going to graph the graph with the transformation. So I am taking my vertex and I am moving it 3 units to the right, 1, 2, 3, and 1, 2 units down. Notice a is equal to 1, so there's no stretch. So I'm going 1 up, 1 over, 1, 2, 3 up, 1 over, 1, 2, 3, 4, 5 up, 1 over, and then the same thing the other way. I hope you guys remember the axis of symmetry that is going to go through the vertex. And the equation for it is x is equal to 3. Oops, right here. And then the coordinates of the vertex, I want you to see the regularity here, the pattern that is going to repeat. The x coordinate is 3 and the y coordinate is -2. Notice, this is your 3, this is your -2. Again, 3 is the x coordinate of the vertex. A lot of repetition here, a lot of patterns you need to notice. I will do example B, and then you will have a good amount of problems to work on. For this one, notice the +1. +1 is going to be, because I am adding, I am going to have, this is going to be shift to the left. -3 is going to be shift down. And the 2 that I have right there is going to be a vertical stretch. Right? So let's see. I am going to start with graphing my parent graph. 0, 0, 1, 1, 2, 4. Again, I hope everybody knows, everybody sees how I do this. Again, you can always plug in the points. 3 squared is 9. Here we go. Use the axis of symmetry. 4, we are 2 away. 3 away. 1, 2, 3. Here we go. This is the parent graph. And now I'm going to move this parent graph around. So let's go start with the vertex. And this vertex is going to be shifted 1 unit to the left and 3 units down. 1, 2, 3. All right, now there's the 2. So normally we would go 1 up to 1 over, but we have to multiply that 1 by 2. So 2 up, 1 over. And then we would go 3 up, 1 over. So we will multiply this 3 by the 2. So 1, 2, 3, 4, 5, 6, 1 over. And I'm going to do the same thing on this side. What might be helpful at this moment is to draw the axis of symmetry. Here we go. This point is going right in here. See how the graph is stretched? I always check because for whatever reason it's kind of difficult to see for me, but if I take 1 and plug it in here, 1 plus 1 is 2, 2 squared is 4, 4 times 2 is 8, 8 minus 3 is 5, and I am exactly at 5, so I know that I did this correctly. Let's take a look at where our vertex is. The coordinates of the vertex are at -1, -3. Again, I want you to see how convenient. This is going to matter, and this is going to matter for our vertex. And our axis of symmetry is x is equal to -1. Again, I want everybody to notice the pattern. Those are the same. All right, you have CD, and then you have 8 more problems to play with. Make sure you reach out, make sure you come see me during my office hours or send me an email. I can meet with you on Teams whenever it's convenient for you, but let me know if you have any questions.